Welcome to X-Ray University. Today we have a very special episode for you. We're going to look at how you go and inspect a PCB. You get a 2D image, 2.5D, 3D, what's the difference between them, and an extra modality we're going to show you today, pseudo 3D. All right, so what's 2D, 2.5D, 3D, and pseudo 3D. This can be confusing, a nomenclature that the X-ray inspection industry has been using for several years now. So the idea for this video is to just clarify this nomenclature so you understand exactly what those things mean. Let's start with 2D X-ray imaging, which is the standard X-ray imaging, the one that if you have a broken arm, you go to the hospital, you get a plate or an X-ray of your arm to make sure if it's broken or not. This is how it works. 2D X-ray is defined when you have an X-ray source. So here's the source in one end. You have a sensor on the other end, and you're going to put your PCB or your sample right here in between the source and the sensor. The idea of 2D inspection is that you have the straight line between the sensor and the source, and your sample is perpendicular to that line, right? So it's 2D. That whole sample is going to be projected onto the sensor. So, and this is an example of a ball grid array or BGA on a 2D X-ray imaging. So as you can see, the distance between the sample and the source here is the same as in here. So you have this symmetric looking image, and voids on this BGA, as you can see in this lighter areas inside each one of the balls. You can see the voids, you have an idea of how big they are, but you don't really know how tall they are, right? Where in Z they are located within the BGA. This is Y, X, and you don't have the Z information coming through. And that's what leads us to the next modality, which is 2.5D. Well, technically a half a dimension doesn't really exist, but the X-ray industry is very creative, and we came up with this half dimension. And 2.5D is nothing but tilting your sample or tilting the sensor. Something has to be tilted to get that side view of the sample. So going back to our board here, if you look, you have X-ray source on the bottom, and one of the ways you can do it, you can have your sample, right? Your PCB is going to be sitting straight or flat in relation to the source, and we go ahead and we tilt the sensor. So the sensor in this case is getting this projection side view of your sample, of your PCB. And here's an example, right? So this BGA, you can see that it's the same BGA I showed you before, but now with a tilted view, you can kind of have a Z dimension of where each one of those voids are. You can't really tell exactly where they are, but you can have an idea of the height of the void because now you're seeing this tilted, this perspective view. Now, I told you how creative the X-ray industry is in creating new things, right? So this is 2.5D or a tilted view. We also created this, what we call pseudo 3D. Pseudo 3D it looks really nice, right? And instead of showing you dimensions in Z, this is actually a 3D view, right? It's three-dimensional because of 3 dimensions being represented here. What we're doing is we're taking that 2D image that I showed you before. We have X and Y, and the Z, or the height in this volume here, is the density of the balls, right? So pay attention, it's not dimension, it's density. So darker, or higher areas here represent the denser areas of the sample, and the baseline here, or the floor in this three-dimensional view, is air, right? Very low density. So as you can see, this representation, this pseudo 3D, gives you some really nice representation of an idea of the shape and the size of the void. But again, you don't get Z information here, you have density information here, okay? That's what we call pseudo 3D, because pseudo is not really 3D, even though it's a 3D representation, but not the 3 dimensions that you were expecting, which is X, Y, Z. We're giving you here X, Y density, right? So that's our pseudo 3D. And there's the last one I want to share with you today is the proper 3D, or computed tomography. And computed tomography is done. We have the X-ray source, the sensor, and we're gonna go ahead and rotate that sample 360 degree between the sensor and the source to get us this three-dimensional volume of the sample, as you can see here. Now you have proper 3D, meaning that the three dimensions are presented here, X, Y, and Z. And you can rotate, you can manipulate. You've seen other videos that will show you how to do that. And what's pretty cool is now those voids that I showed you before, those voids that showed as a flat object on the previous images now shows as an actual volume. You can actually calculate in micrometers cube what is the volume of each one of these voids, and you can pass-fail based on that. Not only you can pass-fail in area, you can pass-fail in volume, which is how much of this BGA is represented by flux or trapped air or whatever else might be inside the BGA that's not solder. The other cool thing about this representation of proper 3D is that you have the location of the void on the ball. A void right in the middle of a solder ball is different from a void that's actually connecting to the PCB or to the BGA. So this is a quick introduction. I hope we'll be able to clarify the difference between 2D, 2.5D, 3D, and pseudo 3D inspection. So next time this terminology comes around, you'll be able to tell them apart. And if you have any other questions, give us a call or send us an email. Visit our website at creativeelectron.com, and do not forget to subscribe. Thanks for watching.